So it's my great pleasure to introduce Yoshiki Masuyama, who has recently rejoined our team. Not recently, like a year ago, actually. He was an intern with us before that, and he did his PhD with Professor Ono at Tokyo Metropolitan University. And actually, Professor Ono was my co-advisor a long time ago, so I guess that makes us PhD brothers. So I'm super excited, really happy to have him on. And he's going to talk about our recent work on spatial audio. Thanks.
So, all right, thank you for the introduction. And it is my great pleasure to be here at SANE. So today I'm going to talk about our effort on the spatial audio modeling, especially using the neural field. So before we dive into the content, I'd like to acknowledge my collaborators. So the 5 people in the shaded area are my current colleagues at MERL, and Christopher is around. Okay, he's in the backside, and is our former intern, and he published several papers with us about spatial audio. And as a quick advertisement, we have just opened several internship positions. So if you are interested in, please ping us after this presentation or just a dinner party. Okay, so here is the agenda of this talk. So let me start with a brief introduction of spatial audio and neural fields. So the spatial audio is one of the long-standing research fields in audio and acoustic signal processing community. It covers a wide range of applications, such as, for example, we would like to analyze a sound field, or like we like to analyze a specific sound field produced by a specific sound source, although there are multiple sound sources. And once we analyze a sound field, we would like to resynthesize it through headphone binaural rendering, or we would like to resynthesize it in 3D world using a speaker array. But we have just started to work on, especially on sound field estimation, because it is a fundamental of the various tasks. So the task of sound field estimation is to reconstruct a continuous sound field in a specific target region using multiple microphones. Also, as shown in the bottom figure, the interpolation of multiple source positions has been studied. These are a bit different problems, but we can apply similar techniques, especially we assume the loudspeaker and the microphone have their omnidirectional directivity. And the more recent studies often tackle both tasks jointly, but then they predict the audio for the new source and the receiver positions from multiple references within the same room. To tackle these problems, of course, there are various signal processing-based methods. In the basis expansion, as you know, the sound field is decomposed into multiple basis functions, such as spherical harmonics or plane waves. Here, the sound field on the leftmost panel is decomposed into the 3 plane waves. Then we can compute the sound pressure at any position analytically. Another approach is panning, so just a weighted sum of the measured audio. This is very efficient, especially for interpolating sound source position if we have a relatively dense measurement. But generally speaking, as usual, the classic methods don't perform well when the measurements are very sparse, so we think about deep learning. Among deep learning, we consider the neural field could be promising because it is very flexible with respect to the source and the microphone positions. Here we define a neural field as a neural network that returns the desired quantity from the corresponding coordinate. For example, NERF predicts the 3D camera. It returns the color and density from the given 3D camera position and the 2D direction. And its advent led to significant progress in the 3D computer vision community. Maybe they go beyond more now. This success motivated us to use the neural field to the spatial audio. For example, the deep impulse response predicts the sound pressure P from the corresponding microphone position R and time T. So such that initial works train a single neural field for each scene from scratch. However, a more recent study leverages the knowledge learned from the training data by sharing a single neural field for multiple scenes. We have explored such the direction for head-related transfer function, HLTF, and room impulse responses, or RYRs. Okay, so let's move on to the HLTF part of this talk. As you know, the HLTF describes an acoustic transfer function from the sound source to each ear in the frequency domain. It contains reflections and diffraction around your ear canal, head, and the upper torso. So by convolving the measured HLTF with the dry source signal, we can control the perceptual sound source position in the binaural audio. Here, interaural time difference, ITD, and the interaural level difference, ILD, are crucial for azimuth localization. You know that when the sound source moves to the left side, the audio reaches the left ear faster with more energy. Meanwhile, the elevation localization mainly rely on the spectral calibration, so some peak and notches. And these clues differ person to person because of the difference in the anthropometric features. So it is ideal to measure your own HLTS with dense spatial grids. But it requires enormous time even with specialized equipment like this. This figure is from the homepage about Sonicom dataset. And we would like to reduce the number of required measurements, and we aim to recover dense HLTFs from the sparse measurement. For this task, HLTF field was proposed to predict the HLTF from the corresponding sound source direction. The input is a pair of the azimuth and the elevation, and the output is the HLTF magnitude for one ear. But you can modify the network to predict magnitude response for both ears or together with ITD or anything. Once it is trained on the discrete measurement, we can predict HLTF at any direction in a griddless manner. This binary approach represents the HLTF for a single subject, but we would like to leverage the prior knowledge of HLTF, but this is just like signal processing yet. So the authors introduced a subject-specific vector to condition the neural field. You know, HLTFs are not significantly different across subject, so maybe we can share the generic neural field across subject. Then we concatenate our latent vector Zi to the network input so that the HLTF field returns a personalized HLTF for a specific subject. Here the I is the subject index. To train this kind of the neural network, first, we train this main generic neural field and a set of the latent vectors on the dataset with multiple subjects, maybe 100 or more. Then, we adapt only this latent vector to the target subject with a few measurements, like 3 or maybe less than 100 directions. And since we can freeze this generic model, we don't need a significant amount of measurement for the target subject. So we can efficiently adapt the pre-trained model to the desired target subject. We extended this approach with more advanced or complicated conditioning techniques. For example, film modulate each fully connected layer by using two parameters, sigma and mu, and they are computed by another small neural network from the given latent vector Zi. And here L is the layer index. And we also took inspiration from the parameter efficient fine-tuning or PEFT, mainly now using the LLM or more generative AI techniques. And I hope that such kinds of approach would be more scalable. In our paper, we explore the bit fit, and it incorporates the subject-specific bias for each layer. And the LoRa employs a subject-specific low rank weights for each layer. And here, we just think about the rank 1 approximation, so that we use a 2-vector U1B. But we can provide a more adaptation capability by increasing the rank. In that paper, we also propose a neural field to approximate some kinds of the IIR filters, and it approximates the HLTFs. So here, our neural field outputs some kinds of the parameters of the backward IIR filters. So the FC is the center frequency, FB is the frequency band, and the G is the gain. So some kinds of interpretable signal processing parameters. Then we can compute their magnitude response by using the differentiable DSP. Then we train the neural field to minimize the reconstruction error of the log magnitude response without the Oracle IIR parameters for the specific direction. And again, we applied the same parameter efficient fine-tuning technique to this neural IIR filter field. We investigated the efficiency and effectiveness of our adaptation techniques on the specific dataset called Footpath. It consists of the HRTF for the 94 subject, where we have the 440 directions for each subject. The training and the evaluation process are a bit complicated, so let me explain the details a bit more. So first, we train the generic neural field and the subject-specific parameters on the HRTF for the 87 subject, and we excluded the 7 subject for evaluation. And in addition, we excluded the 100 directions to evaluate the off-grid generalization capability later. And here, we trained the generic neural field and the latent vector for each of the 87 subjects, and they are optimized together by backpropagation. Then we adapted the subject-specific parameters to each target subject while freezing the shared neural field. We used up to 100 measurements for adaptation and evaluate the performance on 2 test sets. So one is one set consists of the HRTF, and these directions are included in the pre-training set. So we can evaluate how model is adapted to the target subject. On the other hand, the second test set consists of the unseen directions. So we can evaluate together off-grid generalization capability of our neural field. Here is RMSE on the log magnitude spectrum at seen and unseen directions. We compared the 2 different neural field techniques with 4 adaptation method. Here, the Q is the number of trainable parameters, but during the adaptation. So first, regardless of method, if we provide more measurements for adaptation, RMSE just decreased. The performance was improved. But and as you can see on test set 1, the magnitude approach and our IIR filter techniques are almost same performance. And the low rank adaptation performed the best, but maybe because it has a much more adaptable parameters. But you can see the LoRa and the bit fit do not work well at the unseen directions with magnitude approach. We expect that the subject-specific parameters overfitted to the measured direction instead of running some kind of a global feature for the target subject. Meanwhile, our neural IIR filter field is more robust to the unseen directions. Okay, let's move to the next paper. So to empower the new HLTF field, it is desirable to train the generic model on huge number of subjects. So large-scale pre-training always makes things better, I guess. However, the typical HLTF dataset contains fewer than 100 subjects. And even the largest public dataset, SANE contains only several hundreds of subjects. So straightforward approach is to combine multiple datasets to train sometimes HLTF models. And actually, the neural field fit this approach because it is grid agnostic, so we can combine datasets with different spatial grids. But measured HLTFs are affected by differences in recording setups. Here, I show the HLTF on the median plane averaged over the subject in each dataset. These would be close to each other, like between the Hubbard and the REC, but some datasets show the different characteristics, possibly because of the differences in the loudspeaker, microphone, or some post-processing. And the recent study shows the simple SVM can easily classify the original dataset only from the measured HLTFs. So this mismatch would limit the training of the neural field on a combined dataset. To mitigate this issue, we introduce additional dataset-specific parameters in addition to the subject-specific parameters. Here, the dataset-specific parameters are shared across subjects in the same dataset. I mean, the subject from the dataset E1 consistently use the same dataset-specific parameter WE1. While the subject-specific parameter would be changed. And for a subject from another dataset E3, we change both dataset and the subject-specific parameters. Inside of this neural field, I use the BitFit because of its simplicity. For each layer, we select a subject-specific or dataset-specific bias. And we name this approach as a subject and dataset-aware neural field or pseudo field. Here, I'd like to show the qualitative result. The top figure are the TSNA plot for the subject-specific parameters, and each circle corresponds to each subject. The left panel shows the result for the neural field only with the subject-specific parameters, existing method. And you can see cluster for each dataset. That is, the subject-specific parameters entangle the subject-specific information together with the dataset level information like measurement setups. The right panel shows our pseudo field, and where embeddings overlapped each other. So I hope that our additional dataset parameter captures the measurement information. Once we optimize the pseudo field, we can convert HLTF from one dataset to the HLTF as if they are measured in another domain, another recording setups. Here, we convert the HLTF from SANE and SANE and REC to the another domain reference dataset Hubbard. So before conversion, the total energy is totally different, completely different, but the HLTF conversion compensated some global characteristics of the HLTF. But still, you can see some kind small detailed peak and notches are still aligned before and after conversion. So I'd like to say that our conversion still preserves the subject-specific information because I just swap the dataset-specific parameters. Okay, so what we found here is that the additional dataset-specific parameters provide more flexibility for the neural field, and I hope it allows the training of more heterogeneous dataset. Let me move to another work. Here we explore the retrieval augmentation for HLTF field, and we named it RANF. So similar to the previous works, here our objective is to estimate the magnitude response A and ITD tau for target subject S and desired unmeasured direction D. Then to this end, we select subject R1 to Rk whose HLTFs are close to the target subject, at least on the measured directions. So we retrieve some people from the dataset, and their HLTF should be close to the target subject. Then we extract the HLTF magnitude and the ITD for the retrieved subject, but the desired target direction. Then our neural network takes the desired direction D and the retrieved HLTF magnitude and ITD as input. So this neural network converts the retrieved HLTF to the target subject's HLTF. So this neural network should capture the relationship between the retrieved and the target subject. So we compute the low rank weight as a product of the target specific parameter U and the retrieved specific parameter V. So still it's LoRa based. And similar to our previous work, we first trained the main neural field with a set of the subject specific parameters on HLTF of many subjects, then adapt the subject specific parameter to the target subject with a few measurements. The bottom figure shows the HLTF over the median plane, and we upsampled this HLTF from the 3 directions, so front, the top, and the left. Then compared with the neural field without retrieval, our RANF captures more precise structure in the HLTF. Okay. Here are more quantitative results. The orange line shows the result for just selecting the best fitting subject. So this is a retrieval. And our brown blue line substantially improves the performance from that. So it is like our model successfully refined the retrieved HLTFs. And in addition, our RANF outperformed the neural field baselines. So and, we participated in the listener acoustic personalization or lab challenge last year, and ranked first in the challenge. And the task is upsample the HLTF from the limited number of measurements. Okay, so for we see the neural fields for HLTF spatial upsampling and personalization. Several methods share the single neural field across multiple subjects to leverage the prior knowledge of the HLTF learned from the training data. And to scale up the training data, our pseudo field introduces the dataset-specific parameters, and it captures the effect of the measurement setup. But there are multiple papers in such a direction. Sorry, I couldn't talk about the detail due to the time limitation, but we can compensate such the dataset-specific effect by pre-processing. Also, the many method works explicitly or directly predict the HLTFs, but our NIIRF represents the parametric IIR filter to approximate the HLTFs. And such the direction would improve the generalization capability or interpretability, and possibly we can reduce the computational complexity for binaural rendering, because usually IIR filter has more flexibility. Okay, so let's move on to the RIR part. Okay, so as you know, sound propagation within a room is characterized by room impulse responses, or RYRs. And the RYR depends on the source and the microphone position, and it is also affected by the room geometry and the materials. And it involves direct sound, early reflections, and more stochastic late reverberation. So it's actually really complicated. In this direction, neural acoustic field, or NAF, is one of the popular neural fields for RYR. And it takes the source or emitter position, microphone or listener position, together with the time and frequency indices. Then it returns the STFT of binaural RYR for specific listener orientation. So NAF can interpolate both sound source and the microphone positions simultaneously, and it works okay for specific scene, but we need to optimize it for each room from scratch. Meanwhile, INRAS uses the bounce point as conditioning. Here, the bounce point means the point sampled from the room surface as auxiliary condition. So by leveraging the bounce point, we might be able to use a single neural field across multiple rooms by just swapping the bounce point as a condition. But actually, the original paper explored training with only 3 rooms, interestingly. But I will show the effectiveness of the large-scale pre-training later. Okay, so this INRS and its variants predict the time domain RYR, and its training is based on the sum of the time domain and the STFT domain loss functions. So here, the small h is the time domain RYR, and the large h is its STFT, respectively. But usually, both loss functions are independently calculated for the left and right channels, even though the prediction is binaural RYRs. Then the model could ignore the inter-channel relationship, such as the ILD and ITD. In addition, I think the spatial capability of binaural RYRs is somehow limited because usually it relies on the predefined HLTF. So we propose a direction-aware neural acoustic field, or DANF, to model the first-order ambisonics, or FOA RYRs. In FOA RYR, the zeroth order component, known as W channel, encodes the sound pressure measured by omnidirectional microphone. Meanwhile, the first order components, called X, Y, Z channels, encodes the particle velocity along the Cartesian axis. So roughly speaking, our DANF implicitly represents the sound pressure itself and also its gradient at any point. In addition, we propose a direction-aware loss function to explicitly capture the spatial information in FOA RYRs. Specifically, we use the cosine similarity between the intensity vector I, between the ground truth and the estimated FOA RYRs. The intensity vector mainly points to the sound source, especially in the relatively unequivocal condition, and it has been widely used for the sound source localization. So we match the directional semantic information between the ground truth and the estimation. Okay, next, our network architectures just follow the INRS, except where we modify the prediction head to output the 4 channels of the FOA RYRs. And its training is similar to our HLTF strategy. So we first pre-train the single DANF on RYR from the multiple, actually 90 rooms, I guess. Then the pre-trained DANF was fine-tuned on each of 10 holdout rooms with varying number of measurements. And once the fine-tuning is done, we can predict RYRs at any speaker and microphone position for the target room. Here we simulated the FOA RYRs with furnished rooms from the Matterport 3D dataset, and the simulation was performed on the Sound Spaces platform. Here are the errors on several acoustic metrics with different number of measurement and adaptation for adaptation. And so the lower is better. So as a baseline, we evaluated our downf trained on the multiple rooms, but without fine tuning, so the zero shot. But it performs poorly, especially in terms of the clarity score and the early decay time or EDT. This might be because the bounce point only captures the geometric information, and our downf cannot reveal the material information on the target room. And another baseline is we train downf from scratch, cold start. And it works okay if we have tons of measurement, but its performance is limited when the number of measurements are limited. Then compared with these two, our fine-tuning strategy, warm start, achieved much better performance here. And even a single measurement really helps relative to the zero shot, and it outperforms the cold start with the 80 measurement. And we also explored the roller of the pre-trained downf. Here, our motivation is to reduce the number of the parameters for each room, because otherwise we need to store the neural field for each room, and we don't want to save the many of the neural networks. Here, NP indicates the number of trainable parameters for room-wise fine-tuning. And the roller with the rank 1 and rank 3 was applied to the final prediction head, and the parameters are reduced by 99%. Its performance slightly lags behind the full fine-tuning, but they are still better than the cold start when the number of measurement is limited. I think having 800 measurement for each room is a bit impractical. And we hope that this kind of the parameter efficient fine-tuning is beneficial in practical scenarios, and I think now we have more advanced PEFT techniques. So kind of wrap up. So early work such as deep IR or NF train a single neural field for each scene from scratch. And a more recent method, including our downf, shares a single neural field across multiple rooms. Although I couldn't introduce the details, but the recent CPPR work, I think proposed by Meta, it's the model called XRYR, and it can render the RYRs for any source position in any environment. So it is like the cross-room generalization is an active research topic, but it seems more challenging than the case of HRTF because RYR varies more drastically across rooms compared with HRTF across subject. All right, let's move on to the physics informed neural networks or PINs for RYRs. So I'm going to quickly recap a vanilla neural field for RYRs with mathematical formulations. So by fixing the sound source position, the neural field is trained to be a map from a microphone position R and time t to the sound pressure P. The neural field is trained to reconstruct a handful of measurements like this, where D is the number of measurements and L is the number of time samples. And once trained, neural field can render audio at any position in a griddless manner. However, this approach does not consider the physical principles of sound propagation, such as the wave equation. To address this issue, the physics-informed neural network PIN incorporates a soft penalty term derived from the partial differential equation governing the sound field. In particular, the sound pressure follows the wave equation in the time domain, And so we can penalize deviation from it at arbitrary position and time without additional measurements. Here, we can calculate the derivative with respect to the position and time by using the automatic differentiation of the standard deep learning toolkit, because the pressure is now modeled by a neural network. By combining this regularization term and the data fidelity term, pins have improved the reconstruction error at the unseen position compared with the vanilla neural field. So we took inspiration from that and extended our neural field for FOA RYRs down to consider the physical principles behind the FOA. Here is the overview, and our neural network predicts the FOA RYRs from the given microphone position R and time t, and we compute the data fidelity term with the handful of measurement. Furthermore, we compute their partial derivatives with respect to the position and time. Then we penalize the deviation from the two governing the PDEs, the linearized momentum equation and the continuity equation. So let me explain these penalty terms in the next slide. So first, the sound pressure and the particle velocity satisfy the linearized momentum equation and the continuity equation in the source-free region. Maybe we need a bit more assumption, but we usually assume this. Then here the P is the pressure, as I explained before, but U is the particle velocity. Then based on the properties of FOA, we can derive two penalty terms from the equations here. And the W is the zeroth order component of the FOA, and it coincides with the sound pressure P and the SN3D normalizer. So we have some kind of specific scale matter. Then the B is the concatenation of the XYZ channels, and it is proportional to the particle velocity U. Then these two penalty terms should be zero if the predicted FOA completely follows the equations. So we penalize the deviation from them, and then we train PyDown, our method to minimize this regularization term together with the data fidelity term. Here are the box plots of the normalized mean squared error, or NMSE, on the reconstructed time domain RYRs. So we simulated the FOA RYRs by using an extension of PyRoom acoustics called HARP on 10 shoebox rooms with random geometry. Here the red box shows the vanilla neural field without any physics-informed priors, and the green one is some kind of the naive method. Here we apply the wave equation-based prior for the W channel. So it's almost like a existing pin for the sound pressure. So we see the reconstruction accuracy is improved, but the proposed PyDown blue boxes consistently performed better than the these baselines, possibly because of we design two regularization terms specifically for the FOA. Here are more qualitative results. The 5 snapshot of the sound pressure at the specific height. The middle row shows the original target, and the top and the bottom row shows the reconstruction by the naive and the proposed method, respectively. If you pay attention to the after the 25 milliseconds, you can see the naive method results in lower power and sometimes misses some wavefront compared with the original one. But the proposed PyDown accurately captures the wavefront. Here is a summary of the physics-informed part. So interestingly, to the best of my knowledge, the physics-informed techniques usually focusing on the room-wise modeling. So there is no multi-room model or cross-room model with physics information. So like existing method requires us to train new model for each room from scratch. I think the cross-room generalization with some kinds of the physics is one of the interesting and open problem. And also like I think actually the various methods have appeared since the latter half of 2024, and some of them leverages some more coarse approximation of the wave equation or something, and they may be suitable for cross-room generalization because in my experience, the existing PDE-based loss function is good for sample level approximation or modeling, but it's more like sample level modeling. Okay, so let me conclude my talk. So far, we see the neural field for the HRTF and the RYL. We can exploit the prior knowledge of the target sound field in a data-driven manner by sharing a single neural field across multiple scenes or rooms. And the physics-informed methods have also been actively studied, but they have focused on the room-wise modeling. So I think it is worth to explore the cross-room generalization with a physics-informed approach. Also, there remain many challenges such as limited data size, and also like multimodal integration, so how we can condition the neural field or something from the room geometry, material, or other kind of the visual information. But I hope some part of this talk will be helpful to tackle the open problems, and our code, especially for HRTF, is available on our GitHub. Okay, also like a bit again the advertisement, but if you are interested in this kind of the neural approach with for spatial audio, we will organize a special session for neural spatial audio processing in ICASP 2026. So please come to the special session. Thank you for your listening.
All right, thanks. Any questions? Alexei?
Thank you for your talk. In the HRTF section, you mentioned that you are inferring the magnitude responses or interpolating the magnitude responses of HRTFs. What's the practical value of knowing just the magnitude and not the phase or the whole impulse response?
Thank you for your question. I think the predicting the absolute phase is really difficult. So in our RANF paper, we predict the magnitude response for both channels and predicting ITD. Then we can convert the HRTF magnitude or time domain with minimum phase. I think it's very popular in the signal processing. Then we just shift the HRIR to follow the predicted ITD. And like existing metrics is insensitive to the other additional phase information. So
gotcha, and there is some validation that it actually sounds okay.
Yeah, but actually, like I don't have my own HRTF, so like I couldn't validate it. But like I think that would be almost perfect.
Thank you.
One more question?
Yes. Thank you for the interesting talk. My question is around the physics-informed neural field. I was maybe I have missed, or is there a comparison of the computation between the vanilla neural field versus physics-informed? And also, I mean, there is existing numerical methods for solving wave equations, right? So this to be useful, it has to be less computationally exhaustive. Do you have any?
Yeah, thank you for your question. So the inference cost for the vanilla neural field and the physics-informed approach is the same because during the inference, we just go the one forward pass of the neural network. But during the training, we compute this kind of the regularization term and we sample any position and time to compute this regularization term. So we need additional forward and actually backward pass to compute this regularization term. So that during training time, we need more complexity for the physics-informed method. Then the second question, I didn't compare exact simulation with this kind of the neural field, but I think the problem would be a bit different because for exact simulation we need the material information, but our neural field just sample multiple RIR measurement, but so the required information is a bit different.
So the exact room geometry is not of input to this.
Could you say
exact room geometry is not an input to these models?
So in this case, we just input the source position and microphone position time t, and then we train this neural network for the specific room with several measurements.
Right. When you say specific room, how do you describe that into the model?
In this kind of the neural field is optimized for each scene, so we didn't condition this model without any the room geometry or materials. This neural field implicitly runs such the information only from the measured RIRs.
So we'll create a bunch of kind of statistically meaningful IRs based on the training data. Is that how it works?
Yes. Maybe we can discuss more later.
Based on the measured RIRs. The model doesn't know anything about the room. It just knows the few measurements it has, and then it infers the rest of RIRs based on that, without knowing how the room looks like.
So training data kind of dictates the behavior.
Training, I guess, if you call that training, yes. The measured data, yeah.
Yeah. Okay.
Do we have time?
Just one more, yeah, I guess.
Yeah. Okay. So you are using basically L2 error to optimize the HRTF stuff. There's not any perceptual stuff, right? Or
yes, yes, I use just the RMSE on the log magnitude, but actually in this WASPA, the best student paper award, not from me, but he explores more perceptual loss function for that.
Okay, I'll take it offline.
Yeah, thank you so much.
Marco, is it a quick one?
Yeah, just a quick one. For the user conditioned neural fields, do those have to be what are the features for the personalization for that? Is that trained from kind of scratch and just back propagated into user vectors, or can that
yes, we use a back propagation.
I see. So is it possible to get that during inference time without a priori knowledge, or does that have to be fine-tuned for the specific user?
We need to fine-tuning, but possibly we can predict such kind of latent from the head mesh or something.
Is it, I'm curious if there's any work on that.
Yeah, I think it's an ongoing problem in the community.
Gotcha. Thank you.
Maybe at Apple? Talk to Josh, maybe? All right, let's thank Yoshiki again.
Thank you.